Hello and greetings to everyone. Welcome once more to another video in our YouTube channel. In this video, we are going to be looking at the solutions to mathematics paper 2 questions that featured in the competitive entrance examination into the National Advanced School of Engineering Yaoundé in the 2021 session. So the question paper was consisted of 3 problems and the candidates were required to answer all the questions. Calculators were allowed. Alright, so we are going to begin with the first problem, which is problem 1. It was allocated for 6.5 points. Okay, so this is the problem description. It reads, Kasim has a piece of land that is in the form of a triangle OAB with dimensions OA equal to 5 meters, OB equal to 40 meters, and AB equal to 30 meters. After negotiations, he decided to add to each side of the piece of land OAB spaces OAE, OBD, and ABC, all right-angled isosceles triangles with right angles at ED and C respectively. Now, the first part of the question is asking us to determine the nature of the triangle OAB and justify our response. So clearly we see that the triangle OAB is a right-angled triangle because the square of the longest side, which is OA, is equal to the sum of the squares of the other two sides. Since 50 squared is equal to 40 squared plus 30 squared, then the triangle OAB, which is the original piece of land of Mr. Kasim, is a right-angled triangle. So that is our justification. So the nature of the triangle is that it is a right-angled triangle, and the justification is that the lengths of the sides obey the Pythagorean theorem. Now, the second part of the equation is asking us to make a sketch of Kasim's new piece of land, labeling all the vertices. Then later on, we calculate the length of the fence that Kasim will have to construct in order to enclose all his land. Alright, so we are going to begin with the first part, which is constructing or sketching the new piece of land of Kasim. Now, this new piece of land was after negotiations because the question told us that after negotiations, he added to each side of the original piece of land OAB the spaces OAE, OBD, and ABC. Now, these various spaces are all right-angled isosceles triangles with right angles at ED and C. Right-angled isosceles triangles means that it is a triangle that has a 90-degree angle and two sides are equal. Right-angled for the 90-degree angle and isosceles for two equal sides. Alright, so we are going to construct the new piece of land of Kasim. So first of all, we are going to begin with the original piece of land before we add the various spaces that were being added. So the original piece of land was having vertices O, A, and B. That's the original piece of land. Since OA is a hypotenuse, that's why you see the longest side has vertices O and A. Now OB is 40 meters and then AB is 30 meters. Now he added to each side of the piece of land OAB the spaces OAE, OBD, and ABC. So let's first of all start by adding the space OAE. Now OAE is a right-angled isosceles triangle with right angle at E. So the right angle is at E. So it's able to indicate the right angle at E. Next, we go to OBD, which is a right-angled isosceles triangle with right angle at D. And finally, we have ABC, which is a right-angled isosceles triangle with right angle at C. Now, the distance, since these spaces that we added were right-angled isosceles triangles, it means that the distance between for example, if you take the first, which is OBD, the distance from O to D is the same as the distance from D to B because it is a right angle, and then the distance from O to B is the hypotenuse of that right angled isosceles triangle. So we can maybe label it as Y. Next, the distance from A to C, considering the right angled isosceles triangle ABC, the distance from A to C is the same as the distance from B to C. We can label it as Z. And finally, in a triangle OAE, the distance from O to E is the same as the distance from E to A, or the distance from A to E. We can call it X. So we indicate the various lengths in the diagram. Now, the second part of the equation is asking us to find the length of the fence that Kasim will have to construct in order to enclose all his land. So the length of the fence that he will construct in order to enclose all his land is simply the perimeter of the figure that we see. So the length is equal to the perimeter of the figure O, E, A, C, D, B, D, B and D. So the length of the fence is simply the perimeter of that figure, and we know the perimeter of the figure is the sum of the sides. So the length is going to give us OE plus EA plus AC plus CB plus BD then plus DO. Now previously we have seen that word that OE and EA are the same, so I just replace EA with OE. Now we have also seen that AC and CB and BC have the same length, so I can replace CB with AC. And finally we also saw that BD and DO or OD have the same length, so I can replace DO with BD. Alright, so adding the first two terms gives me 2 OE, adding the next two terms gives me 2 AC, and adding the next two terms gives me 2 BD. But we know these various lengths. OE is a length from O to E, which is X units. So we have originally we were told that OB is 40, OA is 50, and then AB or BA is 30. Alright, so since OE is X, we replace OE with X. What about AC? AC is Z and BD is Y. So we have the length of the fence to be 2x plus 2y, or 2x plus 2z plus 2y. Now all we are left to do is to find x, y and z. Then we come and replace here and we find the length of the fence. Now to find x, y and z, we are going to consider these spaces that were being added. We're being told that they are right angled isosceles triangles. From the term right angled, it means that they obey the Pythagorean theorem. So we are going to use each of those spaces. We apply the Pythagorean theorem to find the respective lengths. The Pythagorean theorem simply states that the square of the longest side is equal to the sum of the squares of the other two sides, provided the triangle is a right angled triangle. Alright, so we begin with triangle OBD. It means y squared plus y squared is equal to 40 squared, because 40 is OB, which is the length of the longest side of that triangle. We call it the hypotenuse. So y squared plus y squared equal to 40 squared meters squared. I mean 2y squared is equal to 40 squared meters squared. So y is equal to 20, the square root of 2 meters. Next, we look for x, so we consider the triangle OAE. Since it is also a right angled isosceles triangle, it means it obeys the Pythagorean theorem, which says that x squared plus x squared is equal to 50 squared. So 2x squared is equal to 50 squared, x is equal to 25 times the square root of 2 meters. And lastly, we have the triangle ABC to find the value of z. It is also a right angled isosceles triangle, so we have z squared plus z squared to be equal to 30 squared, meaning that 2z squared is equal to 30 squared, so z is equal to 15 times the square root of 30 meters. Now we replace back the values of x, z and y in the equivalence of the length. So our 2x becomes 2 times 25 root 2, which gives us 50 root 2. Our 2z becomes 2 times 15 root 2, which gives us 30 root 2. And our 2y becomes 2 times 20 root 2, which gives us 40 root 2. The unit is meters. So adding all of it, we have the length to be 120 times the square root of 2 meters. So we can draw our conclusion that the length of Kasim's fence is L equals 120 the square root of 2 meters. Alright, the next part of the equation has a description. We want to, amongst other things, draw an exact figure with the 1:100 ratio. In order to do this, we consider the complex coordinates OUV taking 1 centimeter for 1 unit. The first question, plot the point A in the plane on the ray OU, then the other points B, C and D and E with B above the abscissar axis. Alright, so first we begin by plotting our ordinate and our abscissar axis. The ordinate is a vertical axis and the abscissar is the horizontal axis. Now we plot the point O, which is the origin. Now this is the direction of the vector U, that's a complex coordinate in the horizontal direction. Now since the point A is along that plane, then along the ray OU, then it means the point A is going to lie in the horizontal the horizontal axis. Now what about the point B? It is above the abscissal axis, meaning it is above the horizontal axis, so it is either in this position or in this position, but according to our figure it should be in this position. All right, so with that said, we can now link the various points, and remember this is the original piece of land of Kasim, OAB. Those are the vertices of the original piece of land. OA is the longest side, then followed by OB, then AB. All right, so the right angle is at B. Now we can construct the other points since we have already respected the conditions. Now the other points, we now talk about the other spaces that were being added. So we have OAE, which is right at E. Now in the vertical we have that's the direction. Now we have OBZ, which is right at Z, and finally we have ABC, which is right at C. So that is the construction of the points A and the other points B, C, D, and E, with B being above the abscissal axis. All right, the next part of the equation is asking us to show that Z of C is equal to 1 plus I divided by 2 times Z of A minus IZ of B, provided that a rotation with center C and angle of rotation pi ln 2 transforms the point B to the point A. Alright, so before I get started, I'm going to give you the general representation of all complex transformations in a complex plane. So if a transformation takes the point Z to the point Z prime, then provided the center of the transformation is omega, the scale factor is k, and alpha is the angle of rotation, then the transformation is going to obey this form. But in this case, you are involved with rotations. So for rotations, it means that the scale factor is equal to 1. That is the magnitude of the complex number k e raised to the power I alpha. The modulus of the complex number k e raised to the power I alpha is equal to 1, means that k is equal to 1 because k is the modulus. So with that, we are going to get the general representation of all rotations in this form. Z prime minus omega is equal to e raised to the power I alpha into z minus omega. Z prime is the affix of the image of the points whose affix is z. Alpha is the angle of rotation. Omega is the affix of the center of the transformation. Alright, so with that said, according to this equation, since we are taking the point B to the point A, angle of rotation is pi ln 2 and the center of the rotation is C. So we can let the point A has the affix of the point A be ZA, that of the point B be ZB, and that of the point C be ZC. Now according to this information, it means that if I take the point A and I introduce it into this rotation, then I'm going to yield the point A. So if I take the point B, if I take arrow of ZB, I'm going to get ZA. So ZA is the image, since B is being transformed to A. So with that, in the place of Z prime, I'm going to represent the image, the affix of the image, which is ZA. In the place of omega, I'm going to represent the affix of the center, which is ZC, since C is a center. Now, the angle of rotation is pi ln 2, so I get e raised to the power I pi ln 2 into, in the place of Z, I impute the affix of the point, which is ZB, that's it, because ZB is the affix of the point that is being transformed to ZA. And finally, minus omega, the affix of the center is ZC. Okay, so with that, e raised to the power I pi ln 2 is simply I, because it is cos pi ln 2 plus I sin pi ln 2. Cos pi ln 2 is 0 and sin pi ln 2 is 1. So times I, you just have the imaginary part, which is I. So ZA minus ZC is equal to I into ZB minus ZC. So we can multiply all through by I in the right hand side, and we are going to get this response. Now, since we are proving that ZC is equal to a certain component, then we are going to bring the ZC's together. So adding IZC on both sides, on the right hand side it cancels, on the left hand side I just get negative ZC, which is this guy here, then plus IZC, and then furthermore I'm going to subtract ZA on both sides of the equation. Subtracting on the left hand side it cancels, and subtracting on the right hand side I get IZB minus ZA. Alright, so with that I can rearrange this, and I'm going to get ZC minus IZC to be equal to ZA minus IZB if I divide all through by the negative sign. So dividing all through by the negative sign, I just obtain this equation. Alright, so I can factor out ZC on the left hand side. I'm going to get ZC into 1 minus I to be equal to ZA minus I ZB. Now my ZC, I'm going to divide both sides of this equation by 1 minus I. When I do that, next I now rationalize the complex number 1 minus I. That's I multiply the top and the bottom of the complex number by the conjugate of the denominator. Now since this is 1 minus I, to get the conjugate, I just change the sign of the imaginary part. So it means my ZC is equal to ZA minus IZB divided by 1 minus I times the conjugate, which is 1 plus I, and I divide it by the same conjugate. Now if I multiply the denominators, I'm just going to get 2. If I multiply the numerators, I'm going to get 1 plus I times ZA minus I ZB. So we have proven what was required. Alright, the next part of the equation is asking us to show also that we have ZD equal to 1 plus I divided by 2 into ZB, and ZE equal to 1 plus I divided by 2 into negative I ZA. Alright, so this is a figure that we are interested in. That's the piece of land of Kasim. We constructed this in the previous question. Now this is the representation of all rotations in the complex plane. Okay, so the very first thing is that since we need to prove these two relationships, then the first relationship is relating ZD and ZB, meaning we are concerned just with this right angle triangle OBD. Now it all depends on the individual, because there are so many rotations that we can take into consideration, but I have just chosen one rotation. I'm going to give you many alternatives at the end, and if you try any, you're going to have the same response at the end. Alright, so I can call a rotation R1. The center of the rotation is D and the angle of the rotation is 3 pi ln 2, transforming the point B to the point O. Now how did I get this? It is my decision. I have decided to consider just the triangle OBD, and I am taking the point B to the point O, and the center of my transformation is D. Now it is a rotation. Now I need to look for the angle of rotation. Likewise, somebody could still consider taking the point O to the point B, center D. You still have the same result at the end. Somebody could still decide to take the point D to the point B with center O. Somebody could still decide to take the point O to the point O to the point D with center B. So it all depends on what you want. You're still going to get the same response at the end, because the angle of rotations are going to change. Alright, so the very first thing to note is that if I am rotating in the clockwise direction, then my angle of rotation is negative. If I am rotating in the anti-clockwise direction, then my angle of rotation is positive. Now in this case, what is the angle of rotation? I am taking the point B to the point O, so it means I'm going to rotate from the line DB right up to the line OD. So the angle of rotation is the exterior angle between the two lines, that is the line joining the points D and B and the line joining the points D and O. It gives me the angle of rotation. Remember, the exterior angle and not the interior angle. Clearly the this right angle triangle is right at the point D, so the interior angle between the two lines, that is this line and this other line, is 90 degrees, but that is not our angle of rotation. Our angle of rotation is the exterior angle, as you can see the arrow indicating. So clearly it is going to give us what, 270 degrees, because it is 360 degrees minus 90 degrees, because if we try to complete the rotation, we are going to rotate about 360 degrees, but since the angle here is already 90 degrees, then we need the exterior angle, which is now 360 minus 90, which gives us 270 degrees, which is equivalent to 3 pi divided by 2. So since we are rotating in the anti-clockwise direction, then the angle remains positive. If we are rotating in the clockwise direction, then the angle is going to be negative 3 pi divided by 2. That is in the case where we are transforming the point O to the point B rather. But since I just chose that we should transform the point B to the point O, then our angle of rotation is 3 pi ln 2, and since it is anti-clockwise, then it is positive. Alright, so I can call the rotation that does that the center of the rotation is D, is taking the point B to the point O, and the angle of rotation is 3 pi ln 2. So having all these unknowns, I can just fit in here and I get the rotation, that the complex equation of the rotation that does that, and then I prove what we are required to prove. Now nextly, let's talk about this other proof. You see, we are relating ZE and ZA, meaning we are more concerned with the triangle OEA or OAE. Yes. Alright, so like I said, it is my decision to transform the point O to the point A. It is your decision to do the reverse. It is somebody else's decision to transform the point E to the point A. So it all depends on what you want. It all depends on which is faster. Alright, so I decided to name the rotation R2, having center E and angle of rotation 3 pi ln 2, transforming the point O to the point A. So I'm transforming the point O to the point A. Definitely I must pass through the center of the transformation. Now the angle of rotation is the angle between the line OE and the line EA, and it is an exterior angle, the exterior angle between the two lines. The interior angle is 90 degrees because the right angle of the triangle OAE is at E. So since it is 90 degrees, with the previous explanation, it means the exterior angle is going to give us 360 minus 90, which is 270. So it is equivalent to 3 pi divided by 2. Alright, so with that, since it is also going in the anti-clockwise direction, then the angle is set to be positive. So R2 is a rotation, the center is E, I'm moving the point O to the point A. You could decide and take R2 to be a transformation with center O, moving the point A to the point E. It all depends on you. Alright, so with that now, we let the affix of the point Z be ZD and the affix of the point E be ZE. Since previously we already let the affix of the point B and the point A to be ZA and ZB, and as well the point O is going to have affix ZO as well, and it is just the origin, so 0i plus 0 plus 0i. Alright, so let's begin with our first rotation. Our first rotation takes the point B to the point O. That's what our first rotation does. So taking the point B to the point O, the center of the rotation is D and the angle of rotation is 3 pi ln 2. So we simply replace our image, which is Z prime, with the output, and the output is O. Now the input is Z, which is in this case it is ZB, and then the center is D. The angle of rotation is 3 pi ln 2. So it means I'll have ZO, which is the output, minus ZD, which is the center, to be equal to e raised to the power I 3 pi ln 2 into ZB, which is the input, minus ZD, which is the center. Alright, e raised to the power I 3 pi ln 2 is simply cos 3 pi ln 2 plus I sin 3 pi ln 2, where we know cos 3 pi ln 2 is 0. So finally we get I sin 3 pi ln 2. But I sin 3 pi ln 2, sin 3 pi ln 2 is 90, is negative 1. So times I, we get negative I. So e raised to the power I 3 pi ln 2 is equal to negative I. Alright, so with that, we can now proceed by replacing e raised to the power I 3 pi ln 2 with negative I. So the left hand side, we get ZO, which is just 0, minus ZD gives us negative ZD, equal to e raised to the power I 3 pi ln 2 is just negative I, then times ZB minus ZD. Alright, so with that, we can expand the right hand side. We get the left hand side is negative ZD equal to negative IZB plus IZD. Multiply negative I with ZB and multiply negative I with negative ZD. Alright, so since the relationship we are proving, ZD is on the right hand side, then we can bring every term in ZD to the left hand side. Sorry, it's on the left hand side. Alright, so with that, we get negative ZD minus IZD to be equal to negative IZB. We can divide both sides by the negative sign. We are going to get ZD into 1 plus I to be equal to I times ZB. Alright, so we can divide both sides by 1 plus I. So the left hand side, you just get ZD. The right hand side becomes I divided by 1 plus I times ZB. Now we rationalize the denominator, multiplying the denominator with its conjugate. You just get 2. The numerator, the conjugate of the denominator is 1 minus I, then we multiply with I. So with that, we see that multiplying I times 1 we get I, and I times negative I is negative I squared. But since I squared is negative 1, then negative I squared is just 1. So finally we get our ZD to be 1 plus I divided by 2 times ZB, and we have proven. Now let's look at the second proof. We now consider the second rotation, which is taking the point O to the point A. The angle of rotation is 3 pi ln 2 and the center of rotation is E. Alright, so we just replace our ZA with the output, our ZE with the center. The angle of rotation is 3 pi ln 2, the input is ZO, and the ZD is still the center. Now e raised to the power 3 pi ln 2 is negative I, ZO is 0, so the left hand side still remains ZE minus ZE. The right hand side now you have negative I into negative ZE. Alright, so with that we multiply negative I times negative ZE, just give us ZE. We take ZE to the right hand side of the equation. We factor out ZE from the right hand side. We get ZE into 1 plus I to be equal to ZA. Now since my proof I can see negative I ZA means I just multiply both sides of the equation by negative I, so that I should have already a component in my proof, because I'm working towards getting my proof. Alright, so multiplying the left hand side, I get negative I times ZE into 1 plus I to be negative I times ZA. Alright, so I leave the right hand side constant. The left hand side I distribute the negative I into 1 and into I. So negative I times 1 is negative I, and then negative I times I is negative I squared. But since I squared is negative 1, then negative I squared gives us 1. So finally we have ZE into negative I plus 1 to be negative I ZE. Alright, so with that we get our ZE into 1 minus I by rearranging this to be negative I ZE. We divide both sides by 1 minus I, and then we rationalize the denominator. We keep the negative I with ZA, that is it. We now rationalize 1 over 1 minus I, and we get 1 plus I divided by 2, which is what we are supposed to prove. Alright, so we are proving the two things. Now let me give you some other alternatives. Concerning the first rotation, like I explained, we could still take R1 to be a rotation of center D, the angle of rotation to be negative pi ln 2, transforming the point O to the point B. This time around I am moving from the point O to the point B, so this arrow reverses, and since it is going in the clockwise direction, then the angle of rotation becomes negative. Since the exterior angle here is 3 pi ln 2, then the angle of rotation is now negative 3 pi ln 2. Working it out, you're still going to get this result. We could still transform the points the point O to the point D, and the center is B. You see, so doing it the angle of rotation, I'm going to be going in the anti-clockwise direction, so the angle of rotation is going to be positive. Now the angle of rotation is just the exterior angle between the line OB and the line BD. Since this is a right angled isosceles triangle, it means that and the right angle is at D, then the angle between the line OD and OB is 45. So we have 45-degree angle here, and here we have 45-degree angle. It means the exterior angle here is simply 360 minus 45, which is 7 pi ln 4. Alright, so which is 7 pi ln 4, yeah. So we could also consider that case, and we work it out. You're also going to get the same response. Now considering rotation number 2, you can conclude these are the other alternatives. So if you wish, you can use them to verify if they'll produce the same results, but they are just alternatives. So you should not only rely on what I give. You could still have a different method using any of these alternatives. You're still going to get the same response, and you will not be penalized for any. Alright, so the last part of problem 1 says Kasim wishes that the line OC and ED should be perpendicular and the distance OC and ED should be equal. Determine the algebraic expression of ZC divided by ZD minus ZE. What can be said about the wishes of Kasim? So first of all, we are going to determine the algebraic expression of this, and then now we use that notion to see what we can say about the wishes of Kasim. So previously we have proved that ZC is equal to this quantity, ZD equal to this quantity, and ZE equal to this quantity. So ZC divided by ZD minus ZE, I just replace the value of ZC, sorry. Now ZD is 1 plus I divided by 2 times ZB, then minus ZE. Now we just simplify. You see this, I factor out 1 plus I divided by 2 from the denominator. This negative sign and this negative sign gives us a positive sign. And then in the first term I'm going to get ZB, in the second term I'm going to get IZE. Alright, so these two terms in red strikes off, and then I'm left with ZE minus IZB divided by ZB plus IZE. Now if I multiply top and bottom of this equation by negative I, the numerator I'm just going to allow the negative I, but I'm going to multiply negative I in the denominator. So multiplying the denominator, I'm going to get negative IZB plus I minus I squared ZA. Since I squared is negative 1, then minus I squared is positive 1 times ZA is ZA. So finally the denominator becomes ZA minus IZB. So it equals to the numerator, so they cancel. So at the end we just get the algebraic expression to be negative I plus 0. We can call it maybe equation 1, because it's going to help us to know what to say about the wishes of Casim. Now what does Casim wishes? Casim wishes that the line OC and ED should first of all be perpendicular and then have the same distance. If they have the same distance, it means that the distance from E to D should be equal to the distance from O to C. Now we are going to use some geometry. So for OC, the line OC and ED have the same length, then the distance from O to C should be the same as the distance from E to D. Since we're in the complex plane, we are going to represent OC not as C minus O, because OC is C minus O, but since we're in the complex plane, we use their affixes. So we have ZC minus ZO to be equal to ED is normally D minus E, but we are going to use ZD minus ZE because we are using complex coordinates. Alright, so since ZO is 0, then we just have the modulus of ZC to be equal to the modulus of ZD minus ZE. Now with that, we can divide both sides by the modulus of ZD minus ZE, and we use the properties of modulus. Modulus of this divided by modulus of this is the modulus of the ratio themselves. So the right hand side you just get 1. Now from equation 1, our equation 1, ZC divided by ZD minus ZE is equal to negative I. So the modulus of this complex number on the left hand side is just the modulus of negative I, which is 1. So we clearly see that since the modulus of this guy is equal to the modulus of the ratio is equal to 1, it means that the modulus of ZC divided by is equal to the modulus of ZD minus ZE. But what's the modulus of ZC? Is simply the distance from O to C, and the modulus of ZD minus Z is a distance from E to D. So we can say that the two lengths are equal. So the first wish of Casim has been accomplished. Now for the perpendicularity, we know that for the two lines to be perpendicular, then the angle between them should be plus or minus 90 degrees or plus or minus pi on 2. But the angle between the two lines is just the argument of the complex number ZC divided by ZD minus ZE. But the complex number ZC divided by ZD minus ZE is just the complex number negative I, and the argument of the complex number negative I is negative pi divided by 2. So we see that the two lines are perpendicular. So we can conclude that Casim's wishes have been accomplished. The first wish for the lengths to have the same length, for the lines to have the same length, and the second wish for the lines to be perpendicular, as we can see. So we can conclude that Casim's wishes have been accomplished. Alright, so that was all for problem 1. So we dive straight away to problem 2. Problem 2 was a problem that was awarded for 6 points. The problem reads: consider the following data with variables xi, yi, where xi are marks in mathematics and yi are the distances in kilometers of students' homes from the school. Alright, the regression line of y in terms of x and the regression line of x in terms of y have equations. Those are the reverse equations. First, determine the coordinates x bar, y bar of the average points of the scatter diagram associated to this data. Alright, so simply this is what we are going to do. The average point x bar y bar is a point that solves the system of regression lines. So this is my system of regression lines. I just need to solve the two simultaneously, find x and y. Automatically the x and y becomes x bar and y bar, because that's the definition of the average point. Alright, so from equation 2, I'm just going to replace equation 2 in equation 1. Since the x is in terms of y here, I'm going to take x as negative 1.4y plus 15. So simplifying, we get y to be 0.8y plus 0.8, meaning our and then our y is going to give us 5 when we look for y here, and then replacing y with 5 in this equation. So let us be careful. Here we have missed out a negative. Here is supposed to be negative 1.4. Alright, so negative 1.4 times 5 then plus 0.8, since y is equal to 5. Alright, so with that we get our value of x to be equal to 8. So we can draw our conclusion that the average point in the scalar diagram is the point 8, 5. Alright, the next part is asking us to determine the coefficient of linear correlation arrow and the conclusion we can draw. So the square of the linear correlation coefficient is a product of the gradients of the regression lines. So the first regression line is x is depending on y, so the gradient is negative 0.6. The second regression line, y is depending on x, so the gradient is negative 1.4. So according to the definition, we have arrow squared is equal to the product of those two gradients. So we have negative 1.4 times negative 0.6. So r equal to plus or minus the square root of 0.84. So r equal to plus or minus 0.9165. Now our conclusion is that if we take the magnitude value of the magnitude of r, we are just going to get positive 0.9165, and since it is close to 1, then the scattered points xi, yi is linear. Alright, next, xi are the terms of an arithmetic progression with common difference r prime and first term x1 equal to 1. Determine r prime and x8. So xi are the terms of an arithmetic progression. It means that x of n plus 1 minus x of n is equal to r prime. That's the definition of an arithmetic progression. The difference between any two consecutive terms is a constant. That constant is called the common difference, and in this case it is r prime. Now we have the definition of the first term, which is 1. Now we have to determine r prime and x8. So we are going to use the mean with respect to x. The mean was equal to 8. So we have the mean we know what the mean is. Since we are ending at x8 according to this, then we are just going to find the mean of a set of points or a set of data or a set of a set of points or a set of numbers. Yes, a set of numbers. All we do is that we sum the numbers and we divide by the total number of numbers. It gives us a mean. Alright, so in this case our x bar is going to give us a sum from I equal to 1 to 8 of xi divided by 8, because there are 8 of them. So multiplying both sides by 8, we get 8x bar to be the sum from I equal to 1 to 8 of xi. Now we need to look for this sum. Now this sum is simply the sum of the terms of an arithmetic progression, because xi are the terms of an arithmetic progression, and we know how to sum an arithmetic progression given the first term, the common difference, and the number of terms. We have 8 terms here because we are beginning from 1 to 8. So you are going to get n divided by 2, so 8 divided by 2 into 2a, 2 times x1 plus n minus 1, 8 minus 1 times r prime, because r prime is the common difference. So it means we get 8 divided by 2 is 4, 4 into 2x1 plus 7 r prime. Now we just replace back here. It means that our 8x bar will be equal to 8x1 plus 27, 28 r prime, because multiplying 4 times 2 we get 8, 4 times 7 you get 28. Alright, since we calculated our x bar here, it gave us 8. Then we have 8 times 8 to be equal to 8, because x1 is 1 plus 27 r prime. So 28 r prime is equal to 64 minus 8, which is 56. So our r prime is equal to 2. Now x8 is the last term, thus the n term. So it means our x8 is just a plus n minus 1 times d. That's the definition. So a is x1 plus n minus 1, 8 minus 1, 7, then times r prime. Since we have x1 and r prime, we just replace. Our r prime is 2, our x1 is 1, so our x8 is 1 plus 2 times 7, which is 15. Finally, we get our x8 to be equal to 15. Now the last part of the problem is asking us to determine an estimation of the distance of the home of the student from school whose marks in mathematics is 15. So the marks in mathematics being 15 simply means that I just come to my regression line here. I replace x with 15 because we're being told that xi are the marks in mathematics and yi are the distances. Now we need to look for the distance provided that the marks in mathematics is 15. Nevertheless, we have our x8 to be equal to 15. So our y will be equal to negative 0.6 times 15, then plus 9.8, as you can see. So we get our y to be 0.8 units. Sorry, kilometers, yes, because the distances are in kilometers. So the units here is supposed to be kilometers. So our y will give us 0.8 kilometers. Alright, the next part of problem 2, with a bag contains 8 balls numbered as follows: 1, 2, 3, 5, 7, 9, 11, 13, and 15. A ball is drawn at random from the bag and will succeed when the number of balls is greater than 10. What are the chances of succeeding? So succeeding means that we draw a ball from the bag whose number is greater than 10, because a ball is drawn at random from the bag, and we succeed when the number on the ball is greater than 10. So for us to succeed, then the number should be greater than 10. So maybe we can let the chances of succeeding to be p. Then we are actually looking for the probability. So p will be equals to what? Ns divided by nt, where ns is the number of balls with numbers greater than 10, and then nt is the total number of balls. We know probability is the number of favorable outcomes divided by the total number of outcomes. So with that, we can replace the values of ns and nt. So we need to look for the number of balls that are greater than, whose numbers are greater than 10. So clearly it is 11, 13, and 15. So we have 3 balls with numbers greater than 10. How many balls were there? There were 8. So it means our probability of succeeding, that is the chances of succeeding, is just 3 divided by 8. Alright, next description. The previous draw is made 10 times, putting back the ball in the bag after each. Let capital X be the random variable giving the number of successes after the 10 trials. Determine the probability law of x and calculate E of x and V of x. So E of x here is the expected value, which is the same as a mean. V of x here is a variance. Alright, so clearly x follows a binomial distribution. Why? Because firstly, the number of trials is independent. Secondly, the probability of succeeding is constant for each trial. Those are the most important points. So it means x follows a binomial distribution. Now if you're following a binomial distribution, it should be defined in terms of the number of trials and the probability of succeeding. So the number of trials is 10, the probability of succeeding is 3 divided by 8. So the probability law, the probability of x equal to small x is equal to, you just write the formula, n 10 combination x, because 10 combination x, the chances of succeeding raised to the power x is 3 on 8, and then the chances of failing raised to the power n minus x, 10 minus x. But we can relate the chances of succeeding with the chances of failing by this equation, because it is either you succeed or you fail. So since the probability, the maximum value of probability is 1, it means p plus q is equal to 1. Q is the chances of failing. So it means q will be equal to 1 minus p. Since p is 3 on 8, q becomes 1 minus 3 on 8, which is 5 on 8. That's why we find 5 on 8 here. So this is the probability law. Now since it follows a binomial distribution, then the expected value is just the number of trials times the chances of succeeding, which is 10 times 3 on 8, which is 15 on 4. Now the variance is the number of trials times the chances of succeeding times the chances of failing, which is 10 times 3 on 8 times 5 on 8. Simplifying, we get 75 divided by 32. Alright, so that was that for problem 2. Now we move on to problem 3. Problem 3 was allocated for 7.5 points. Alright, so problem 3 reads: a complex plane with orthogonal reference system OUV is given. Let alpha be a real number in the interval 0 to 2 pi. Okay, solve in C the equation z squared minus 2z sine alpha plus 1 equal to 0. So we are just going to apply our quadratic formula here. So our z will be equal to 2 sine alpha plus or minus the square root of 4 sine squared alpha minus 4, all divided by 2. Alright, so with that we factor out 4 in the square root. We get z to be 2 sine alpha plus or minus the square root of 4 into sine squared alpha minus 1, all divided by 2. Now the square root of 4 is 2, so we have this scenario. Now the 2, we can factor out 2 from here and 2 from here. It cancels out with that in the denominator. We get our z to be sine alpha plus or minus the square root of sine squared alpha minus 1. But sine squared alpha minus 1 is just negative cos squared alpha. It means my z equal to sine alpha plus or minus the square root of negative cos squared alpha. Alright, so with that, the square root of negative cos squared alpha is the same as the square root of negative 1 times the square root of cos squared alpha. Since cos squared alpha is positive, then we are good to go. Now the square root of negative 1 is a complex number I, since we are solving in a set of complex numbers. So our z becomes sine alpha plus or minus I times the square root of cos squared alpha, where the square root of cos squared alpha is just the absolute value of cos alpha. So it is positive when cos alpha is positive and negative when cos alpha is negative, since alpha is in the interval 0 to 2 pi. Next, we consider the points A and B with affixes z equal to sine alpha plus I cos alpha and zb equal to sine alpha minus I cos alpha respectively. Write za and zb in the exponential form. Alright, so we are going to begin by writing za in the exponential form. So to write in the exponential form, you just need the modulus of a complex number and the argument. So z equal to sine alpha plus I cos alpha. It means that the modulus is the square root of the sum of the squares of the imaginary and the real parts. So we get the square root of sine squared alpha plus cos squared alpha. But for any angle alpha, sine squared alpha plus cos squared alpha is an identity, which is 1. So the square root of 1 gives us 1. So the modulus of the complex number A is equal to 1. Now we need to find the argument of the complex number A. Now to find the argument of the complex number A, first of all, is the angle that the complex number makes to a positive real axis. So to find the argument of a complex number, we need to know the quadrant to which the complex number belongs. Now the complex number A belongs in many quadrants depending on the value of alpha, because cos alpha and sine alpha might be positive and negative at the same time or at different times. So when that happens, then the argument of the complex number A changes. Alright, so I'm just going to plot, indicate, we use some ranges of alpha, and then we get the argument of the complex number A. Alright, so I'm just going to sketch the graph of sine alpha and the graph of cos alpha. That's what we are going to do. Alright, so here we go. I'm going to sketch these graphs in the interval 0 to 2 pi. So let's begin with sine alpha. Let me make it to be bigger. Right, so just follow up, because it is very important to know the interval in which those guys are positive and the interval in which those guys are negative, because without that you might be tempted to just assume that they are in the first quadrant, and then you just have one answer. Alright, so this is in the interval 0 to 2 pi. That's cos alpha in red. Now let me use a different color for sine alpha. So now in the interval 0 to 2 pi, sine alpha looks like this. Not really good, because my hand wasn't stable, so I'll just try my best again. Alright, so I hope you guys are really enjoying the video. So do well to subscribe to the channel if you have not done so. Alright, so we know that in this interval here is pi on 2, because that's when cos is 0. When sine is 0, it is pi. When cos is 0, it is 3 pi on 2 now. And when sine is 0, it is 2 pi. Here our cos is 1. Right, so here you have 1. Though this sine graph was supposed to cos and come to 1 a bit. Anyways, let me just explain. Alright, so we see that what if alpha, this is this alpha, then this is the graph of f of alpha. Yes, f of alpha. Now this is for y equal to the cosine of alpha, and then this is for y equal to the sine of alpha. Alright, so first condition, if we're in the interval 0 right up to 2 pi, we see that both graphs lie above the abscissa axis, so they are positive. So it means that the complex number a is going to lie in the first quadrant, because both the real part and the imaginary part are positive. Alright, so with that, we are going to get that for alpha in the interval 0 to 2 pi, to 0 to pi on 2, sorry, we get that the argument of a complex number is just tan inverse of cos alpha divided by sine alpha, because it's in the first quadrant. But cos alpha divided by sine alpha is the same as cot alpha, and there's an identity that cot alpha is tangent of pi on 2 minus alpha. Alright, so it means I just get my argument to be tan inverse of tan of pi on 2 minus alpha, which is pi on 2 minus alpha. So my complex number a represented in the exponential form is just the modulus, which is 1 times e raised to the power I times the argument. The argument is pi on 2 minus alpha. Okay, now we take the next interval. So we take now this interval. So in the interval pi on 2 right up to pi, we see that what the cosine is negative because it is below the abscissa axis, but the sine is positive because it is above the abscissa axis. So the cosine being negative, meaning that the y coordinate, that's the imaginary part, is negative, and then the sine being positive means that the real part is positive. So if you just have something like this, x being positive means x is here, y being negative means y is here. So it means the complex number is going to fall here. So this is a fourth quadrant. So in the fourth quadrant, we have that the argument is just negative tan inverse of cos alpha divided by sine alpha. So that's why it was very important so to note that. Alright, so let us proceed. So we are going to indicate all the other cases, and then with respect to the sine, so with respect to z of b, I'm going to do some, and then you do the rest to see if you have understood, and you post your answers in the comment section. Alright, so for alpha in the interval pi on 2 to pi, we see that you just have the argument to be negative of the argument of za to be negative of tan inverse of cos alpha divided by sin alpha, because it's in the fourth quadrant. So since the tan inverse is just pi on 2 minus alpha, it means negative of it becomes alpha minus pi on 2. So my za becomes this. Now in the interval pi to 3 pi on 2, we have this scenario. It falls in the third quadrant, because doing it, you see that the sine is negative and the cosine is also negative. So with that, we get our argument to be pi plus tan inverse of cos alpha divided by sin alpha. So we get 3 pi on 2 minus alpha. So this is a exponential form of za. And lastly, in the interval 3 pi on 2 to 2 pi, we see that it falls in the second quadrant, because the sine is negative but the cosine is positive according to our graph. So we just get pi minus tan inverse of that quantity. We get pi on 2 plus alpha. So this is the exponential form. So that's it. Now writing b in the exponential form, the same story. If my this might be z of b is sine alpha minus I cos alpha, the modulus is the same thing, which is 1. Now if alpha is in the interval 0 to pi on 2, we saw that both cos alpha and sine alpha were positive. So this complex number here is going to fall in the fourth quadrant, because since cos is positive, then negative of it will be negative. So x is positive and y is negative, so in the fourth quadrant. And the fourth quadrant, the argument is just negative tan inverse of cos alpha divided by sin alpha, which is alpha minus pi ln 2. So ZB is equal to e raised to the power I alpha minus pi ln 2. So we clearly see that what this complex number here relates with our this complex number here. But now here alpha is pi ln 2 to pi, here alpha is 0 to pi ln 2. Next, if alpha is in pi ln 2 to pi, then both cos alpha and sin alpha, you know their signs, so the argument is just going to give you pi ln 2 minus alpha. So you need to do it to get this answer. Make sure you get this answer. So we are going to get this. So your assignment now is to verify when alpha is in pi, in interval pi to 3 pi ln 2, what is ZB, and when alpha is in interval 3 pi ln 2 to 2 pi, what is ZB, using all the notions that we have used. Alright, so the next part of the problem reads: let f be a transformation in the plane that transform each point m of the plane with affix z to the point m prime of the plane with affix z prime, such that z prime is equal to I z bar. Given that z is equal to x plus iy and z prime is equal to x prime plus iy prime, with x prime and y prime in a set of real numbers. First question: express x prime in terms of x and y. So what happens is that my transformation f transforms the point m with affix z to the point m prime with affix z prime, such that z prime is equal to I z bar. Now z bar is just a conjugate of the complex number z. So having z to be x plus iy means that z bar is equal to x minus iy. That's the conjugate of x plus iy. So since this respects the transformation, then z prime, we just replace it with x prime plus iy prime equal to I into z bar x minus iy. So we multiply all through with I, we are going to get x prime plus iy prime to be ix plus y. We rearrange, we get x prime plus iy prime to be y plus ix. So we equate the real part and the imaginary parts together, we are going to get our x prime to be equal to y, because it is a real part on the left hand side and y is a real part on the right hand side. The imaginary part on the left hand side is y prime and the imaginary part on the right hand side is x. So we get x prime equal to y and y prime equal to x. So with that, we have expressed x prime and y prime in terms of x and y. Next, show that the set delta of the point m having coordinates x, y, that the self image after the transformation f is a straight line, and find the Cartesian equation of this line and the vector expression of its slope. Okay, so if the set of points m are self images, then f of m is equal to m, meaning that if I introduce m in my transformation, I'm also going to yield back m. So inputting m, all points m, the result will give us m. Those points are called the invariant points, and the line we are going to find is going to be called the invariant line. Alright, so m has coordinates xy, so the complex form is x plus iy equal to I into since it follows the transformation, then we have x in the place of z prime, we are just going to replace with x plus iy, because it's the image is still m. Next, z bar is x minus iy, so we have I into x minus iy. We multiply all through with the I, we simplify, we get x plus iy to be equal to y plus ix, meaning that equate the real part, x will be equal to y, equate the imaginary part, y will be equal to x. So x equal to y and y equal to x boils down to y is equal to x. So the set of points delta, the set delta of points m has Cartesian equation y minus x equal to 0. Now that's the equation of a straight line. Now the next is that we are going to find the vector expression of the slope. Now what is a slope? First of all, the slope of this line is just a change, that's the derivative with respect to x, so of y. So dy by dx is just equal to 1. So that is dy by dx, but we need the vector equation. So I'm going to display to us what we are going to do to get the vector equation. So we need the angle, because I'm just going to call the line OA the length of the gradient. Yes, so I need to write the line OA in terms of in the vector form. Yes, that is what we need to do. So we need the angle since we already know the magnitude. Alright, so I'm just going to characterize A with coordinate x and y, and then we look for x and y. Horizontal distance is x and vertical distance is y. From SOHCAHTOA, the length is 1. From SOHCAHTOA, we know that the cos theta is equal to the adjacent divided by the hypotenuse, so it's x divided by 1. Sin theta is opposite, which is y, because it's the same as this divided by the hypotenuse, which is y divided by 1. So with that, we get cos theta to be x and sin theta to be y. Now tan theta is what? Is simply the change in y over the change in x, which is a gradient. So y minus 0, because y minus 0, for y0 is 0, divided by x minus 0, x0 is 0. So it means our dy by dx is equal to y minus 0 divided by x minus 0. So tan theta is equal to y divided by x. So y divided by x is the same as dy divided by x, dy divided by dx, which is tan theta. So it means our tan theta is equal to 1 clearly. Alright, so the point A having coordinate x, y can now be characterized by the point A having coordinates cos theta sin theta, because the x is cos theta and the y is sin theta. So writing the vector form, this OA here is actually the vector equation, the vector expression of the slope. We are going to bring it back here and we express it. So we are going to get the x coordinate times the direction plus the y coordinate times the direction. So the x coordinate is cos theta times the direction plus the y coordinate is sin theta times the direction. Now we need to look for theta. Our tan theta is equal to 1 because it is dy by dx, meaning that our theta is just tan inverse of 1, which is pi divided by 4. So it means my vector equation of the slope E, as it was given, is cos theta u plus I plus sin theta v. But theta is pi ln 4, so we get cos pi ln 4 u plus sin pi ln 4 v. So finally, cos pi ln 4 is root 2 on 2, sin pi ln 4 is root 2 on 2. So we can factor out root 2 on 2 and we get E to be root 2 on 2 into u plus v. Alright, so these are some useful information that we are going to use to solve the next part of the problem. So finally, show that for any point M having coordinates xy, the vector mm prime and E are orthogonal, and that the midpoint of the segment, when you do this, know that it is a segment. The segment mm prime is always in D. Our D was all lines that are self images. What is then this transformation F? Alright, so first we are going to show that for any points M, the vector mm prime and E are always orthogonal. So first we need to look for the vector mm prime. So the vector mm prime is m prime minus m. So m prime has if you write it in the vector form, remember this we are going to write it in the complex coordinates because we are being given complex coordinates. So x prime with the unit vector in that direction, and then y prime with the unit vector in that direction. So our x prime goes with u plus y prime goes with v. That gives us m prime then minus m, because m prime has coordinates x prime, y prime, m has coordinates xy. So we have minus x u plus yv. Now we group the u's and the v's together, we get x prime minus x times u plus y prime minus y times v. But what do we know? We know that our x prime is equal to y and our y prime is equal to x. So with that, we get this, because m was being transformed to the point m prime under the transformation f. So we get our mm prime vector to be y minus x times u plus x minus y times v. Now if the two vectors are orthogonal, it means that the dot product is equal to 0 by the definition of orthogonality of two vectors. So we need to look for the dot product. So this is for mm prime, and then for e, we have e as root 2 on 2 into u plus v. So we just write root 2 on 2, root 2 on 2. That's the column form. Alright, so finally we multiply y times root 2 minus x times root 2 plus x times root 2 minus y times root 2. So y times root 2 minus y times root 2 is 0. Negative x times root 2 on 2, sorry, plus root 2 on 2 times x is also 0. So at the end, we get that the dot product of the two vectors is equal to 0. So we can conclude that the two vectors are orthogonal. Next, we need to show that the midpoint of I, the midpoint which is I of the segment, like I said, when you see this, know that it is a segment of the segment mm prime is always in D. So the midpoint of I is having coordinates, let's just say AB, where A is what the sum of the the x coordinates of M with that of M prime divided by 2, and then B is the sum of the y coordinates of M and M prime divided by 2. Now since for I to be in Z, then B should be equal to A, because Z is the line y minus x equal to 0. Sorry, delta is a line y minus x equal to 0, meaning y is equal to x. So here you have the y coordinate is B and the x coordinate is A. So proving that I is in delta, meaning that we just need to prove that B is equal to A. Now since we have our x prime to be equal to y and y prime to be equal to x, as you can see here, it means that my A becomes, in the place of x prime, I'm going to replace it with y. So I get A to be y plus x divided by 2. Now what is my B? In the place of y prime, I'm going to replace it with x, so I get x plus y divided by 2. So since y plus x divided by 2 is the same as x plus y divided by 2, then A is equal to B. So we can conclude that I, which is the midpoint of the segment MM prime, is always in my line delta. Finally, we have to determine the real number alpha for which the point A is not in delta. So first of all, for the point A to be in delta, then cos alpha should be equal to sine alpha. Why? Because this is the point A. It was given as ZA equal to sine alpha plus I cos alpha. So the point A, this is the affix, so the point A is A, the x coordinate is sine alpha, the y coordinate is cos alpha. So if it belongs in delta, it means that the y coordinate is equal to the x coordinate. So if it does not belong, it means that the y coordinate is different from the x coordinate. So all we need to do is to solve this inequation. Alpha is in the interval 0 to 2 pi, 0 being included, 2 pi being excluded. So cos alpha different from sine alpha means cos alpha minus sine alpha different from 1. If you write it in the form arrow cos alpha plus lambda, you're going to get the left hand side to be root 2 cos alpha plus pi ln 4. The right hand side you have 0, so that is different from 0. So it means that the cos of alpha plus pi ln 4 is different from 0, meaning that the cos of alpha plus pi ln 4 is different from cos inverse of 0. So our cos inverse of 0 plus or minus 2k pi, if you wish to do so. So cos inverse of 0 is not pi n, but rather it is pi ln 2. So we have multiply this by 2, and then plus or minus. So the plus or minus goes for the because it is PV plus or minus 2k pi. So I'm just going to leave that to you to complete it. So at the end, you take it and you intersect with alpha in this region, in this interval. So from here, you're just going to get alpha to be different from pi ln 2 minus pi ln 4 is just negative pi ln 4, because you subtract pi ln 4 on both sides of the equation. So negative pi ln 4 plus or minus 2n pi. N is an integer. Alright, so when n is equal to 0, you just get negative pi ln 4, but alpha is in a positive region, so you remove that value. When n is equal to 1, you get let's take the positive part, 2 pi minus pi ln 4, you get the value. When it's equal to 2, you get the value when it's 3, and then you intersect with 0 to 2 pi, and you get your response, the values of alpha for which A is not in delta. Alright, so that is all about the video. Make sure you subscribe to the channel, turn on your notifications, because more videos are coming. So in the next video, we are going to be looking at the solution of Polytech paper 1, Polytech 2021 paper 1. The remaining questions, because question 1, exercise 1 and exercise 2 were already solved, so we are left with 3 more problems to solve. Now for those who are writing Polytechnic Douala, before you write your exam, we are going to upload the video solutions of Polytechnic Douala 2021 maths section. Alright, so see you guys in the next video.